Actually, this one we don't have to stream. I think I told them that we will not stream. So, but would you like to stream or
Do whatever, I don't care.
okay. But maybe let
I mean, I have a recording of this from FSTT. So.
Okay. Okay.
So yeah, I'm going to talk about linearly ordered coloring of hypergraphs. So basically, specifically 3 linearly ordered colorable hypergraphs. And this is a joint work with my advisor Anand Lewis and Alan Newman. Okay. Okay, this works. So you may know that what graph coloring is. I mean, just saw it. And I must remind you, like hypergraph coloring, we are just looking at coloring where each edge is non-monochromatic. So these problems are very quite hard, even for graphs. We know quite strong hardness of approximation results. So generally what we do is assume some structure on the graphs or hypergraphs. So for example, for graphs, we assume, let's say it's 3 colorable and try to color the graph using minimum number of colors. For hypergraphs, we typically assume, let's say it's 2 colorable. Okay. Now, what we are doing here is studying a sort of different notion of coloring for hypergraphs. So here we are not looking at monochromatic edges, but we are trying to color using some linearly ordered set. I will just use natural numbers. And for us, proper colorings would include edges where you have a unique maximum. So here the vertex 8 is the maximum and it occurs once. To make it clearer, this is something which is not allowed because 8 occurs twice and 8 is the maximum, right? Okay. And even for us, starting from a 2 linearly ordered coloring, a colorable instance would make sense. And the reason we're looking at this problem is so two is this instance is 2 linearly ordered colorable. 2 colorable in the linearly ordered colorable sense. Okay. So the point is the reason we are looking at this problem is people were studying all these notions of approximate coloring. Like you looked at 2 versions of coloring of hypergraphs. One was the standard one where there was no monochromatic edges. The other one was the linearly ordered coloring. You could come up with other generalizations, right? And all those generalizations are captured in this thing called a promise constraint satisfaction problem, right? And these people were studying these problems and they sort of came up with the almost complete characterization of these problems. The only gap seemed to be this particular version.
Approximation.
No, it's not an approximation gap in the sense it's like.
As in like they are looking at characterizing approximability or characterizing that.
Okay. They are trying to solve the addition sort of gap problems. In some sense, they are gap problems, yeah. Okay. Right. So before we started, this was the best known result for 2 linearly ordered linearly ordered colorable hypergraphs. And what we were able to do is color using n to the power 1/5 colors using some SDP rounding based approach. And simultaneous work was able to do it in 2 log n colors. But actually, our approaches can also, by some simple modification, get this result, except for the constant. Anyway, so the proof of this result is actually simple. I think I will be able to say something about it in 3 minutes. So let's say you have a 2 yellow colorable instance and you take the colors to be -1 and 1 instead of 1 and 2. It's the same natural linear order. And you'll realize that the hyperedge, if it's properly colored, then the hyperedges satisfy this constraint. Okay. Now, what you can do is relax it to a SDP. Okay. So replace the integers using some unit vectors, and they sum up to some vector minus V naught. Okay. And even for this SDP, the ideal solutions should look something like this. But obviously, we may get completely bad solutions which look like this, which have no information about the actual coloring. But what we sort of want to do is stare at the solution and get something out of it. And one way to get something out of it is look at the projections onto the V naught vector, right? And maybe if we have large projections, we get a lot of idea about what is the proper coloring. So to make this sort of idea precise, if you look at the projections, they also satisfy the constraints we had. The gammas sum up to -1, and the gammas are at most 1. But the difference is they are not integers. Okay. And now our algorithm just uses these gamma values and tries to extract independent sets iteratively. So in the first iteration, so the gamma values lie in this interval of -1, 1. And the first iteration will divide the interval in half. And then we'll observe that this set can be colored using the largest number. Basically, we can color it using n, let's say, right? And you can show that this coloring can be extended. Okay. In the second iteration, we'll do the same thing, but okay. This should have been the set we should stick with, not the other one. I just made a mistake with that direction. And keep doing it. So it's sort of a bisection kind of thing we keep doing. And at the end of some iterations, we'll end up with a very small interval, right? And by that time, we have just used log 1 by epsilon colors. And for the remaining remaining vertices, what we did was some standard hyperplane-based rounding-based methods. But if we had used some random perturbation and repeated the same thing, a probabilistic sort of argument would show that we would have colored every vertex. That's it. So there are some directions you can work on if you would like to.
Arka, are there any questions?